Hello everyone, and this is for our USA EE533 lab 6 demo video, and we made a four thread, like a multi-thread CPU, six-stage pipeline based on ISA, so that we can transfer the S code to our CPU. And this is Hobo, and I'm going to show you our four thread code. And we this is our pipeline. So, and the very beginning, we documentation our instruction support. We support for the basic arithmetic instruction like the add, sub add, and or left shift. And this is a basic arithmetic instruction. Also, we support branch instruction like B and BL. Also, the BX, that's also the branch equal and branch not equal, which means we support both unconditional and conditional jump. And also the store word and load word, which inside the ARM structure is the load register and the store register here. So this is the basic SA we support, and under this is our six-stage pipeline. And first is pipeline control. After that is if stages. Inside the if stage, implement our instruction memory. Also, we do the fourth thread logic to increase the thread ID for selecting PC from thread 0 to thread 3, which is thread 1 to thread 4. Okay, so when we come to the ID stages, we have the code here. So actually, we put the instruction, we divided them into some logics to make this logic come to later. We can use this control signal to do our instructions. Okay, so for after that, also in ID stage we have register files, and inside register file we have the IFRF, which is internally forwarding register file. So I don't like to show too much details. We already have this on our GitHub. You can check later. So after that we go into EX stage. In EX stage we have a ALU, and we use the decoded ALU control signal control to ALU to support our calculations, and our calculations support both signed and unsigned format. Okay, so come to the mem stage, and inside the mem stage we have the data memory, and the data memory is also the symmetric memory, not the symmetric, synchronous memory. Okay, so then it's the read back, and read back is just a conditional logic. It's read back to ID stage to have some read back signals. And uh, also in the ID stage, we calculate the branch address and to catches to the EX stage. And in EX stage, we actually do the branch instructions, and we do jump and conditional jump, stuff like that. And also we do the test bench. And here is just an example for us, for you guys. And this is for like a one thread and for the multi-thread code. And this is just an example for for each one threads. And we use a no-op to change other threads for doing this program on multi-thread hardware. Okay. So it will take a lot of time to run this test bench, and I just show you guys the result. So in the log file, we can see the all task is all passed. So it means this test bench can be run successfully. And after 26 seconds, we can see that the last D memory is the 9 memory. It showed like 323, which is just the biggest number inside this test bench, so it's correct. We can see at very beginning, the 323 is at very end. So after sort is going to be the highest part. So the whole array is being sorted. So Let me pass to the Yukun. He will show us how to transfer the ISA to transfer the .s file, .s file to our instructions.
I paused. Yeah, you can share. I'm not sharing screen. Wait,
I need to stop sharing.
fine. And give me your.
I need to.
Check. Wait a minute. Wait a minute. Here. Okay. Are you recording?
Yes.
Okay. Okay. Hello. I'm showing our ISA and our scripts for transfer from ARM code to our own pipeline design. This is a helper for the 32 bits in our pipelines design. You could watch it at the very end. It which shows that the first 3 bit is condition and the 2 bit defines different methods and you could watch it in these 3 parts. So basically our design is based on these helpers and and then we could show you our scripts. The first script is that we do our first filters to filter all the necessary code in in our ARM code because it may comment something or something is just useless. So this code is for the first select and after first select we could have this is the all the code that is necessary. Yeah, it's like this. And then we are using this map. Let me check. We are using this map to mapping the ARM code to our own code. So firstly, we don't write data memory before generating bit file with an .xoc file. We just have an software interface so that we could do data memory write and data memory read. So we will translate all the dot. Wait a minute. We will translate all the dot words into dot memory read so that our 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 software uh is more flexible. And then this all code is all about that helper. It's just a mapping. And this disk is for branch. I will explain it later. We need 1, 2, 3, 4, 5. We need 5 disks to handle the branch. And the major part is firstly, we will reset. We will do the reset the necessary register to 0 because you couldn't because they will start with random numbers if you don't do reset. And then we will find if and then we will find all the labels. We will find all the labels because all the labels is for branch. Yeah, we will find all these labels, this .l2, .l3, .l0. This is for the potential branch. We will need to find these zeros and then we execute line by line. And this is the major part and it's it's just some combination. And I will explain how we do the branch. The branch is because we know how we do branch from the ARM code, but we don't know how we do branch. Like where is the PC of some of the branch before you could execute it? So we don't know that. So what I'm doing is we use a disk to mapping the ARM codes line and then when we execute it to deadlines we will let me check. When we execute it to deadlines we will store deadlines to a new disk and at the very end we will find from the new disk that where is our target PC so that we could recreate it that line again. So the basic logic is if we don't find the target when we executed this branch, what we do is we write wait for execute to deadline, and at the very end we will watch this not found label list to execute them again. This is all our one step match, and you could use different offsets to explain it to a four thread. Just use 0, 1, 2, 3 in different places. So there's a big problem is that the ARM code is byte based, means it multiple force for each increase, but our design is 64 bits for a single address. So if we want to do mapping, we are going what we are going to do is we don't change the ARM codes by mass. So what we are doing for first thread is like we first write the first thread. You could see that our data memory is increasing by 4. And then this is the first thread code. It's up to 112. And then this is the second thread. This is second thread, and we write from 15913. This is the second thread, it's to and for the third thread we write to 2610. This is the design because we don't know they are executing address or they are executing data. So it's impossible to do these changes, so we just keep it. But it still have nothing to to block us to doing the first threads. And Rohit will show you how we do it on the NetAPJ.
Hi everyone, I'm Rohit. Now I'll show you a bubble sort implementation on the processor that we have developed. As of now, you can had explained you like how to from a C code how to generate the binary file. And now I'll write the binary file that you can generated into the IMEM instruction memory and data memory of on the FPGA using memory mapped registers. So first, we have this base script, so which takes the inputs like the memory address, data address, and the value that needs to be returned to that particular address. So this is the like usage of the script. So we can write a data or instruction to particular address using these commands, and we can reset the PC, and we can stop and start running of the processor. And this is we have one more usage like a step wherein like only one cycle will be advanced, so it will help us for debugging. And we have these inputs like register all reds and debug, so that we can debug uh, how a processor is working. So this is about the base script, and using the we have extended we have scripts which use pipereg.pl. That means scripts that use this script as a like a reference script and runs does multiple things at once. So let's say uh, we have uh, this script which basically so this is nothing but the binary of the bubble sort that we have. And as you can see, this is the data memory of the uh, data memory. So we have from address 0 to 9, so these are unsorted uh, data that we are giving, and we'll be sorting this by running our program. And this is our instruction memory, and this is a binary uh, code that's generated by the scripts that shown earlier. And this is the script that writes these binaries to the given data and address memory. So first, let me load the bit file. So this is our bit file having multi-thread processor. So in this first example, I'm just running the program. Currently, the program is on thread 1. So currently, I'll be running the program. So we have our instruction memory. We have segregated into 4 parts. So thread 1 starts at 0, and thread 2 starts at 128, thread 3 on 256, and so on. So currently the entire program is on thread 1. So it starts from instruction memory 0 and goes till 128. Not completely till 128, but it's occupies till 128. So and other three threads are empty. So that don't do anything in this example. And in the coming example, will show like we'll load all the four threads with like four instruction memories, like four threads with uh, all four programs, and we'll try to run all the threads parallelly in the next example. Okay. So I have uh, loaded the FPGA, and now I am writing the instruction and data memory. Wait, why is it? Wait. Yeah. So currently now I'm writing D memory and instruction memory and data memory to the block RAM. So and yeah, now I'll do PC reset, and now I'm running the processor. So I'm waiting for some time for it to run. Uh, and I'm stopping, and I want to demem and I want to read at what's there in the address 0. So this is so let me like read everything I have. Yeah, so right now in the address D memory of address 0 of D memory, we have this value. This is the negative value, and this is the smallest of all the numbers. So we have one more script that reads everything that's there on the data memory, and let's run that. Sorry, data mem read. So this will read all the values in the data memory from 0 to 10. Yeah, so these are all the values from 0 to 10. So let me uh, dump dmem. Yeah, so these are the final values that's there in the D memory. So as you can see, these are now sorted. As you can see, the first is like smallest negative number, and at the end you see the largest uh, uh, value. So and now we'll show how the Uh, yeah, in the second example, we'll be running like four programs on four different threads. And here in our example, we are running sorting same program on different threads, and but we are running on different data. So I'll just show you the binary or like assembly code of our program. So when yeah, this is our code. Yeah, as you can see, this is the data memory. So it has like unsorted data. Like this is the first set of data, like which is going from 0 to 9, and next set of data that's going from 10 to 19. So this is unsorted. You can see it has combination of like both odd and sorry, positive and negative numbers, and till 39, like we have four sets of data, and this is our instruction memory. So first thread, the instructions will start from address 0. As you can see, these are the instructions that are starting at address 0, and like the program ends here, like for the first thread, and here like have added like knobs so that like we are not executing any random instructions in the thread 1, while thread 2 and thread 3 and well remaining threads are being executed. And from here, like the thread 2 program starts. So As you can see, like it's starting from 080 hex. That means it's from 128. Uh, and yeah, and here, like we have equally divided the instruction memory into four parts. So from here it's thread 3, and similarly from here it's, yeah, 1 8. Here it's thread 4. So these are and you can see I have added knobs where when the program ends. So yeah, so this is our instruction and data memory, so that will be loading into the instruction memory and data memory of the processor. So it's getting loaded. Okay, so it's done. Now let me run the program. Yeah, so this is PC reset, and let me run the program. And now I'll halt the program. Now let me read the data memory again. So for that also we have we are using the same script. So okay, okay, let me yeah, so this is the final contents of the data memory. As you can see, uh, as you can see, the first 10 values are sorted, and as you can see, the next 10 are also sorted. So yeah, we were able to run like 4 different programs on 4 different threads in this lab. Yeah, thanks for watching, and thank you all.